No, there's a quiz tomorrow.
So the quiz is on 11/7?
Everything since the last quiz. Yeah, so today we're actually in chapter 12. So we actually finished chapter 11.
So I guess a homework is due for that too.
Correctamundo. If I finish.
Everybody's start hysterical crying like. The class are both sobbing math students.
So the test is on Tuesday. So I already posted the practice problems, so practice those over the weekend. We can probably talk about some of them on Monday, and then Tuesday would be the test. I would say anything that 11.7 homework is due tomorrow, but for like chapter 12 homework that I finished today and tomorrow, that homework is not due till Wednesday, right? So I really want you guys to focus on the test material. So, yeah, that's that. But chapter 11, you have to do the homework because you're going to be tested on. Right, so test 2 covers chapter 11. And the practice problems are right here.
Do it more.
Let's talk a little bit about integrals from calc 1 and 2. How did we develop them? Yeah, that comes from the fundamental theorem of calculus, the genius of Newton. But like when integration was first starting, what did they use it for? Basically to measure area under curves, right? How did they do that?
Riemann sums?
Riemann sums, how did they set up a Riemann sum? Right, so how you did it in calc 1 and 2 was developed using Riemann sums. Right, so basically what happened was they tried to figure out the area under a curve, so they had this random curve, and they wanted to find the area under that curve from A to B. Right? And because this thing might have some weird shape that you don't automatically know a formula for, they couldn't really find the area directly. So what they did was they decided, well, let's use something that we do know how to find the area for, which was rectangles, right? Which is easy, length times width. And how they did it was they broke this guy up into sections, and on each section they used a rectangle, right? To estimate the area of this thing by using the area of the rectangle that was under the curve, right? Now they could choose that the rectangles are defined by the right endpoints, or by the left endpoints, or by the midpoints, or by some other rule like Simpson's rule or trapezoid rule or anything like that, right? But it was all to somehow approximate the area under this curve, and it didn't actually give you the exact area. Some space might be missing, or you might get an overestimate sometimes. But this was basically the idea. And the idea was if you could somehow use an infinite number of rectangles, you'd fill in all the gaps and everything would give you the exact area. So that was sort of the idea. In Calc 3, we have a very similar idea, except now, since we're one dimension up at least, we're going to be doing double integrals with two variables. We're not going to be able to find area now. We're looking at something higher. Volume, right? So the integral that we're going to look at now is going to be a way to get to a volume of something. So we're going to use sort of the same idea. We're also going to use Riemann sums, but now we're going to be in 3 dimensions. So we have some surface hovering over here. Right? This is our f of xy. And we're going to want to be able to integrate over some region that's in the xy plane, like whatever. Right? Now, how do we do that? Well, similar to how we do Riemann sums, we're dissecting into rectangles. We're going to dissect that region into rectangles. Well, I want them to be parallel to the axes. Right? Right? And on each one of these rectangles, we can erect a box, right? That's going to cut into this thing, right? So there we can do like tons of boxes all over the place, right? And it's our equivalent of a Riemann sum in 3 dimensions. Now they're not rectangles, they're actual boxes. And what the idea we're going to use is we're going to take a region, we're going to cut it up into boxes. On each box, on each rectangle, we're going to cut it up into rectangles. On each rectangle, we erect a box, and we can approximate the volume under that curve by using the sum of the volumes of these boxes, right? So that's sort of going to be the idea. And again, we're going to be able to pick which corner of the box we want to touch the surface, and we can get different approximations. And then we're going to take a limit to get, you know, the actual volume under the curve. But that's sort of where the basic idea is coming from. So I just want you guys to appreciate that. We're not going to do a lot of work with that, but we are. I wrote all that down in notes, but I'm not going to write it down here. I just want to explain it to you so you can sort of see where we're coming from. Right? So now we can look at the notation of what this thing looks like. So we're going to look at two integrals here. You put the function after that, and then dA. And this is a very generalized integral, right? Here, R defines the region of integration. And we're going to be able to make this very specific to the region that we're looking at, right? So in this example that I drew here, this region, I can call it R. Right? And so they said, double integral over R of this function dA. And dA is just the differential in two variables. Right? So just like in general our integrals had like a dx or a dy at the end of them, here we have a dA, and basically it can represent either dx dy or dy dx, right? In other words, the order is going to matter. You're going to be able to integrate with respect to x first and then y, or y first and then x. That's how we're going to do this double integral. We're sort of going to split it up into two things, right? Now, again, we could do the formula using these guys. Should I write that down? I don't think I should write that down. I should probably skip that. Okay, that's the notation. I think I should write it. Now, suppose R equals AB on a CE, right? You might see this notation in the book, and what that really means, it's the set of all points such that your x is between A and B, and your y is between C and D. Right? Which is like our last example. If I give you a limit on x and y, you're defining a rectangle. So, I have two. I can have a rectangle R. So this is A to B. This is C to D. That sort of defines our rectangle, right? The A and B gives you the limits on the x, and the C and the D give you the limits on the y. You end up with a rectangle. And again, what we're going to do is we're going to cut this rectangle up. Then we're going to choose what points we want to touch the surface if we go to that height, right? So So then we're going to get these rectangular boxes, and then we're going to measure their volume, right? So now, suppose, what's the notation for this? So we can think of each thing here as a change in x, think of each thing here as a change in y, and so I can define the change in area to be the change in x times the change in y. Right? And then I know that the volume is going to be equal to, what's the volume going to be equal to? Area times height. So it's going to be, the height is going to be given by the function at some coordinate. Right? So this is the height at point I, y, I. Right? So I can pick this point for that particular rectangle that I'm looking at. Pick the point x, I, y, I. Right? And so now I can find the volume of that by finding the area of the rectangle multiplied by the height, which is given by the function, which you're going to be given the function. And so we're going to be able to define the integral in the following way. So that's going to be the limit. Go to infinity, and we're going to do a double sum. I should probably use it. These coordinates are different. X, I, Y, J. Right, the J enumerates the Y levels, and the I enumerates the X levels. Yeah.
I have a question. So where you wrote dA equals dx dy or the opposite, does the order matter?
The order will matter. We're going to talk about that later. I was just mentioning. We're going to talk about that later. The order is going to matter. And yeah, times delta 8. Right? So we're pretty much adding all these rectangles. We assume that we can get an infinite number of them. We're going to multiply the i's by the j's. We're going to add them all together, creating this sort of double sum, and that's going to give us what the integral is. And it's possible for something to not be integrable. It means this limit doesn't exist. As far as the definition, though, we're hardly ever going to use that. And this is sort of our way of finding a generalized area, which is volume. Generalized volume. Don't want to labor too much on Riemann sums, but I should give you one example. So in this case here, our rectangle looks like 0 to 3, 0 to 2. Right? Now I want to divide it into 6 equal rectangles. How can I do that? One way I can split this into 2, split this into 3. So there are 6 equal rectangles, and I want to take the right-hand corner as endpoint. So I'm going to take this, 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 this. And so this is for the rectangle 1, rectangle 2, rectangle 3. Doesn't matter how you number them. We're going to add them all together.
Are those squares?
They would be squares, yes, 1 by 1 squares. Square is a special type of rectangle. So now what we do, we can actually measure f at all these points, right? So here, our delta A is equal to 1, right? So it's a 1 by 1 squares. So double integral. So V is equal to the double integral over R of this function. Which is approximately equal to, I'm going to find the sum. So it's going to be delta A times the sum of all these heights, right? So it's going to be f of, what's the points? This point is?
1, 1.
1, 1. Then 1, 2. Then I can do, so this is 1, 1, 1, 2, 2, 1, 2, 2.
3, 1, 3, 2.
3, 1, 3, 2. So this is going to be 1 times, so now this is going to be 4 plus 1 plus 1 plus 4 plus 1 plus 4 plus 4 plus 4 plus 1 plus 4 plus 4 plus 4 plus 4 plus 9 plus 1 plus 4 plus 9 plus 4. So this would be what? That's 6 plus 9 plus 9 plus 12 plus 14 plus 17. What's that? Your arithmetic buffs. So that's 18 plus 12.
30.
That gives you 30.
61.
67?
67.
Huh?
67.
Okay, cool. So that is the approximate volume in whatever units you're measuring things in. 67 cubic units. In math, you don't really care about the units that much. That's the physics class. That's how you approximate. Now let's look at how we can do it exactly. So we're going to talk about iterated integrals, which means like multiple integrals. The trick is sort of like how we did partial derivatives. We're going to sort of do a partial integration. Right? So you can look at this guy, integral over r. So, for instance, so you're given an integral like this. Now remember, when you integral, you're finding volumes. You will be given limits, right? So pretend that these are limits, these are constants. And now instead of my dA, I want to explicitly write, if I'm doing dy dx, meaning I want to integrate the y first or the x first. You can look at it as a to b. And then on the inside, you do that c to d and y. So that's sort of how we're going to do the integrals, one at a time, right? We're going to do the inside integral, and then we get a result, and then we do the outside integral, and we break it down like that, right? So, and these guys are going to be constants, just like everything else will hold. Fundamental theorem of calculus, it all holds. We're just doing it one variable at a time. That's how we're going to break these guys down. And c to d, a to b, of my f of x, y, dx, dy. I could actually look at this as doing first integrate from a to b of f of x, y with respect to x, which means I'm thinking of y as a constant while I'm integrating the x's. Then when I plug these limits in, because it's a dx integral, the limits are going to be plugged into the x values, so now the x's are going to become constants. Then you're going to end up with a function of y, which you're going to integrate with respect to y. So, I mean, when I do an example, it'll be clear. We'll figure
Why don't you write r there under the two integrals?
Oh, so this here, I'm specifying r.
Oh, okay.
So here, r I'm saying is equal to the rectangle ABCD, right? Now what that means is that my x value goes from A up to B, right? And my y value goes from C to D, right? So what you see here is like when I'm doing the integral on the y, my limits are from C up to D.
Mm-hmm.
But if I'm doing the limits on the x, it's going from A up to B, right?
Okay.
So anything that looks like here where A, B, C, D are constants, right? That really means that R is a rectangle. Right? The limits on each integral is describing what each variable is doing. So it's saying here I want to integrate the y going from C up to D, the x going from A up to B.
Yeah.
Right?
Thanks.
So that's a good question. I neglected to mention that. So
I guess all of these would be considered definite integrals.
yes, these are definite iterated integrals.
Okay.
Which are the fun ones. Most of the time we're going to be integrating definite integrals.
And indefinite just don't have a region specified.
Right. And then you're going to have two constants of integration. Those are sort of where, most of the time we're going to know where we want to integrate. Let's do a couple examples so you can see. No, writing down the theory. No one learns from theory, typically. So look at those two. So basically what's the picture here? I have a region. What's the region look like?
It goes from 0 to 1 in the x-axis and from 1 to 2 in the y-axis.
0 to 1 in the x-axis?
You said that's the inside of the x.
This one?
Right, so you match up, the d's match with the integral. So inner matches inner, outer matches with outer, right?
So,
Oh, I'm
So this
sorry, I
is
thought
dx.
you drew the arrow to that one. Sorry.
Oh, well, I'm talking about both of these. They're,
Oh, okay.
so it looks like,
So in that one, the x would be 1 to 2.
right,
and
so
the
we
y
know
would
here
be
I'm describing a
0 to
region
1.
where x goes from 1 to 2 and y goes from
0 to 1.
0 to 1, right? So I'm really, there's a rectangle over here. And what I want to do is I want to integrate this function, which means whatever this graph is, find the net area under that surface that's over this rectangle, right? That's basically what I'm asking for here. So here's how we're going to do it. One at a time, right? We're going to evaluate the inner one first, then the outer one. First few times we're doing this, we're actually going to write the brackets to emphasize what I'm doing, but eventually you won't do this. Right? So that's what you're going to do, right? Now, what's the integral of this with respect to x?
X squared.
X squared over 2. This is a constant, right? So it just stays, right? So this is actually x squared over 2 y cubed, right? Now this you want to evaluate between 1 and 2, right? You're doing all of that, right? And it's just calc 2 happening in the middle, right? Calc 1. Right? Now, this is 0 to 1. So fundamental theorem of calculus says you're going to take the 2 and you're going to plug into the x, right? Because we're doing dx, right? Take that 2, plug into that x, and what are you going to get? 2y cubed minus,
1/2.
you take the 1, plug into the x, that's 1/2 y cubed dy. So this is really 0 to 1, 2 minus 1/2, that's 3 over 2 y cubed dy. And so now you only have a function of y, the integral dy. So you integrate that. What's the integral of that?
Y to the 4 over 4.
Y to the 4th over 4. So we get 3 over 8 y to the 4th, which is evaluated between 0 and 1, which is just going to be 3 over 8. Okay. So if you see an integral like this, you go work your way from the inside to the outside, right? So I have dx dy means I want to do the dx first. So first I think of x as the variable, y as the constant, do my integration, fundamental theorem of calculus, all that, done, right? And remember that when you're doing dx, your constants get plugged into the x, right? Then we're going to have something, the result we're going to have to do it with respect to y, and then so on and so forth. How about this one? Here we want to do the y first. So I'm going to do 0 to 1 of xy cubed dy dx. This is going to be x, y to the 4th over 4, between 0 and 1, x.
1 over 4.
This is going to be 1 over 4, y to the 4th. Sorry, yes, I'm plugging word. We just did dy, so we're plugging into the y. Right? And so now we can integrate this, because it's just a single variable integral, right? What we're used to. What is the integral of that?
X squared over
X squared over 2, right? Which times the 4 is going to give us 8. I'm going to go between 1 and 2. If I plug in 2 here, I get what?
4.
Right, 4/8, which is a half, minus
1/8.
1/8.
So 3/8.
This gives you 3/8. If you guess that that wasn't a coincidence, you are correct. If you're integrating the same thing over the same region, it doesn't really matter which variable you choose to integrate with first, right? Now there are some tricks with this in the next section, but for the rectangle, it's actually not that bad. You can literally just switch these if you want when these are constants. If they're not constants, which they won't always be, you can't do that so easily, but we're going to talk about that later. But this is it's called Fubini's theorem. It says if f is continuous on r equals a b by c d, then double integral over r of f of x y dA is equal to ab cd f of x y dy dx, and it's actually going to be equal to, when you flip the guys, cd ab f of x y dx dy. They'll both give you the same answer. That's Fubini's theorem. I can write this down, but it's not really going to be something that I've heard more generally. It doesn't matter what order. And sometimes it actually makes a difference what order you pick. Let me show you an example where. So for constants, if they're always the same, why would you choose one over the other? I'm going to show you an example.
More generally, this works if f is bounded on R and discontinuous on only finitely many smooth curves.
Yes.
Example, look at this guy. The region over R of y cosine xy, and A, where R is 0 to 1 by 0 to pi. So now look at how we can do this. In one case, y cosine xy. I can do the x first, the y second, in which case I would do 0 to 1, then 0 to pi, versus I can do the y first and then the x second.
Question.
Yes.
We're given just the R with the range that it's over. Should we assume that the left?
Yes, always the x's and this is always the y's. Yeah, this is the notation for working. Now I know in the case where our limits are all constants, I can just switch them and not worry about it, right? Now the question is, why would I want to switch as opposed to not switch? Right? Would it actually make a difference in evaluating these two integrals? What do
Yeah,
think?
then you wouldn't have radians if you did the 0 to pi first. You have
It's not a matter of radians or
radians in here.
Like, how do you do this integral? Let's work on this one. What would this be?
I think I see why, because in the second problem, you have y as both an argument and as a function.
Correct.
And that's why
So if you're evaluating this integral, what would you have to do?
you have to do this integration by parts.
Integration by parts. Do I need integration by parts here?
No.
No. Right? What do I need here? Well, x is just in the cosine, so I can just integrate that, right? So I have 0 to pi. What would be the integral of cosine xy with respect to x?
X squared over 2 times y.
What?
Times, oh, wait, no.
Sine
Sine
x.
I'm all the way here.
Sine of xy.
Y squared.
No.
Y squared
Oh, no.
over 2 sine xy.
Okay.
There you go.
This was the point of the diagnostic test, people. Okay, so you're integrating something like, let's make it easier, cosine of 3x. What would you do? What's the integral going to look like?
-1 over 3 sine.
No, not like
Minus sine.
No, it's sine.
Positive 1 over 3 sine 3x, right?
Yeah.
Because you do the substitution, which by the end of calc 3, you don't do substitute with this anymore. You just know there's going to be a third that comes out, right? Because that's the constant.
Yes.
Cosine xy.
Oh, 1 over
One
y.
over y.
1 over y
Sine
sine of
x.
xy times this y, the y goes away.
Goes away.
Right? And that's between 0 and 1. Now I'm going to plug that 0 and 1 into which variable?
X.
Into the x, right? Because I just did dx. So I'm going to take the 1, plug into here. I'm going to get sine y. Take 0, plug into here. Sine of 0, 0. And now what's the integral of sine?
Negative cosine.
Minus cosine between 0 and pi. Cosine of pi is what?
A 0.
1, negative 1.
Negative 1 times the negative gives you positive 1. Then you minus cosine of 0 is?
1.
1, which is negative.
Right, but there's a negative, so it's a negative 1, so the answer is 2. I'm afraid to actually do the integration by parts. Yeah, it's the same thing, right? The y might as well have been 3, 4, 2, pi. It doesn't matter, right? It's a constant. Okay, let's see. You choose u and dv, right? In this case, what would you choose as u?
Cosine.
U is
U would be the y. dv would be the cosine xy. How do you know which one you want to pick?
I generally want to choose the.
Liate, right? right? Logs, inverses. This is algebraic, which basically means polynomial. I don't know why they, because putting a P here, you couldn't pronounce it. Right? So you need like the vowels there. So this is trig. These are exponential.
How we got to say, I
Right?
like a liate.
And then here, this guy, U first. And then you go down, right? Which means if you have a mixture of any of these functions, the guys higher in the list get to be U before the guys lower in the list. Here, you notice that polynomials come before trig. So you choose U to be the polynomial function, and the other guy gets to be the trig function, right? If I was mixing a log and a polynomial, U gets to be the log, right? The polynomial would be the dv, etc. Right? Calc 2. Okay. Let's move on. You guys can try it. I'm not. I mean, if it shows up on a test, I'm not, you know, of course I hold you responsible for it. I'm not gonna.
Of course.
I'm just saying. Right? So the order does matter, and it's not a matter of, you know, one way is hard and the other way is easy. There are cases where one way is impossible, and then the other way, oh yeah, that's not so bad. Right? So just be aware of that. Those are some really nice examples of those are in the next section when we look at general regions. So everything here we're doing over rectangles. Things actually change a little bit when you do things in general. Example? I think those would be so earlier I asked you to estimate an integral. Yeah, here it is. So of f of x, y equals 4 plus x squared plus y squared over 0.3, 0.2. Okay, now try that. We did that estimation with the Riemann sums. Now actually, I want the exact volume. I mean, the algebraic properties of double integrals are very similar to the single integrals, right? You can factor constants out, you can split an integral across a sum, right? Integral respects the order of inequalities, that sort of thing. There's one trick that does come in handy that if you can actually separate the variables completely, you can actually split the product. So what I mean by that is, if you can look at this as a function of x times a function of y, then you can literally break them apart. F of x dx times g of y. An example of that one. Okay, what was the exact volume? 15?
5-0.
5-0. What did we get before? 60 something? Okay. So how do we find it? Volume is equal to
Double integral.
a 4 plus x squared plus y squared, right? Now which order did you use?
Dx dy.
Actually, it doesn't even really matter. They look sort of symmetric. So let's say dx dy. What are the limits I put on here?
0 to
No.
0 to 3.
0 to 3, right? Because my x is the inner one, has to match with the inner limits, right? And then the y limits go on the outside, which is 0 to 2. So what I do is I first integrate this with respect to x, right? So my y is a constant, the 4 is a constant. How do you integrate constants? Integrate 4 plus, and then this.
X was
Between 0 and 3, dy. So I plug in 0, everyone 0, plug in 3, I would have 12 plus 9 plus 3y squared. So 12 plus 9 is 21, you integrate that, you just get 21y plus y cubed, between 0 and 2. So you get 42 plus 8. So the actual error is 15. So our last one was an overestimation of the value. Yes?
Can you say rules apply, like if you did a left-hand approximation, it would be
It
underestimate?
completely depends on how your function looks. Right, so even in the 2D case, it would matter, right? So if you're looking at a function that looks like this, if you do a left, it will be an underestimate, right? But if the function was curved that way, if you did the left, you'd get an overestimate. Right? So it really matters what your function looks like. You can't really tell right off the bat. And it's sort of harder here unless you can draw the surface and the region properly, which you tend to not be able to do. But this one we could actually draw, though. What's that? What does that look like?
That's a paraboloid.
It's a paraboloid. Okay, how does it look?
Opening up.
Starts at z equals 4, right? And then opens up. Right? Now I just want to find the volume under that guy. Between x equals 3, so at 3, and then y equals 2, right? So we're basically asked to find the volume of that thing. Right?
So
and
that
it's actually
volume
50.
goes, but what about the height of the volume? Does it go from
The
4
height is
to
given by
wherever?
f of xy, right?
Okay,
And I want it over the region of this rectangle, right? So I just start at this rectangle and I go up until I hit f of xy. Right?
so you're taking the whole, not just the bottom of the parabola, but all of that?
The bottom of the parabola all the way down to the
Okay.
xy plane. Just like how in 2 dimensions, you're measuring the area from the curve all the way down
Okay,
until you hit the x-axis.
If the surface crosses under the plane, or will that ever?
Yeah, then it will give you a negative volume. The
But
same sort of thing
Would we,
happens, like a
would we
net
like
volume.
add it? So it would be the net.
Yeah, it would be the net volume. So it's going to be the positive volume minus the volume that's underneath. Alright, so these are the properties. Make sure you write them down or just remember them. They're pretty similar to the properties you had from Calc 2, Calc 1. The difference is here, remember the integral product is not the product of integrals. However, in the case where you can separate the variables of x's and y's into completely separate functions, you could separate them, right? And why does that work? Why do you think this works? Yeah, so let's say I'm doing this guy, f of x, g of x.
Oh my god.
he fainted.